Howdy, it's Unit 2, Part 2. We are almost done with Unit 2 as a whole. This is Module 8, Radioactive Decay and Conservation of Mass in Nuclear Equations. Alright, radioactive decay, what is it? It is the spontaneous release of radiation by unstable nuclei in order to increase stability. Okay, so radiation can be either energy, just energy by itself, which is gamma, or it can be energy accompanied by a release of a particle. That's all other forms of the decay that we're going to look at. So what are the forms of radioactive decay? We got three main ones that you and I are going to look at here, and it's alpha decay, beta decay, and gamma emission. So alpha decay, you release an alpha particle and energy. Beta decay releases a beta particle and energy. Gamma emission is just a release of energy, no particle associated with it at all. The other three are positron emission, electron capture, and neutron emission. You can look at those definitions for just your own research. So let's talk about alpha decay. So it's typically found in heavier nuclei, and the means to achieve stability is to reduce mass. So whenever you want to reduce mass, alpha decay is generally the route the nucleus is going to take. So the nuclei will shed mass in the form of a helium nucleus to become more stable. And the helium nucleus that is released is ionized, meaning it has a charge. It's actually positively charged. And it's called an alpha particle. So alpha particles are positively charged, like I said. They don't have any electrons whatsoever. Alpha particles are very massive, but they actually travel pretty slow. So they have what we call a low penetrating power. So they can cause significant tissue damage if you're not shielded, but fortunately you can shield yourself from alpha particles with clothing or paper. Pretty easy. So let's look here. We have an alpha decay here where a particle is coming off of plutonium-240. You can see that 240 and 94 atomic number plutonium, and the alpha particle is coming off. It's got two protons and two neutrons. And what the result is you have a uranium-236 nucleus left over. Let's move on to beta decay now. It's common in a nuclei of any size where instability is caused by the number of neutrons. So if we're just trying to increase stability because we have too many neutrons, beta decay may be the route that we take. So a neutron actually is going to decay into a proton and an electron. This is a neutron from the nucleus. It decays into a proton and an electron. The proton stays in the nucleus, and what happens is the electron leaves the atom, and that electron that leaves the atom is called a beta particle. So let's see what that looks like. So first, let's know a beta particle is negatively charged, just like an electron. The mass of the nucleus actually remains unchanged. It doesn't change the mass whatsoever. Beta particles have very low mass but are traveling at very, very high speeds, and that can actually penetrate through skin and cause some deep tissue damage. So now we're going to see what it looks like here. Alright, so we have a beta decay. Don't worry about where it says neutrino on the top there. What we're going to focus on is the bottom part where it says beta particle. You can notice that the mass between the two nuclei does not change. It stays at 228. But if you notice, the atomic number increases from 88 to 89. Because a beta particle has zero mass but a -1 atomic number. Let's talk about gamma radiation. The nucleus is going to undergo gamma radiation and become more stable through release of just energy. Sometimes when all it needs to do is release energy, this is what it's going to do. There's no change in mass, and there is no change in the element whatsoever. The gamma radiation can actually be reduced by shielding, but you cannot stop it. There is no shielding. It is the highest frequency and highest energy form of radiation that we know of. It's usually found with another type of decay, but it doesn't always have to be. Now, one thing that can happen is if you're exposed to far too much gamma radiation or anything like this, it can be very, very severe. And what can happen is you end up looking like this guy. Okay, I don't want that for you. You don't want that for you. Certainly nobody at Stony Point wants this for you guys. So just be very, very careful if you ever come across some gamma radiation. So looking at this radioactive decay comparison here, the three main types, alpha, beta, and gamma. You have the particle that they're associated with, the mass and charge of those particles, and the penetrating powers. As you can see, Alpha has low penetrating power all the way up to gamma, which has very high. And I want to point out, on the far right, transmutation. That means, is a new element formed? When a nucleus undergoes alpha and beta decay, a new element is formed. When it undergoes gamma emission, no new element is formed. So it's a really good idea to look at this just to make sure we understand everything and how it plays together. So here's shielding. You can see alpha, beta, and gamma, and what actually shields each one of these pretty well. If you notice, paper shields against alpha, plastic and skin and those kind of things shield against beta. Steel and lead pretty much can't even stop gamma radiation. It might lower its energy, but really nothing can stop gamma whatsoever. All right. So quickly we're going to segue into carbon dating and half-lives here. The half-life of carbon, we need to mention, carbon-14 is what is used for carbon dating fossils and things like that. Half-life is 5,730 years plus or minus 40 years. That means basically the amount of carbon-14 decreases by 1/2 every 5,730 years in whatever you're measuring. In most cases, it's fossils. What happens to carbon-14 is that it decays into nitrogen-14 through what is beta decay. And you can actually see the equation for that right below here. So pretty interesting. That's how we use carbon dating. So now we're looking at balancing nuclear equations. This is really something that you're going to have to be able to do very easily. And we want to show you how to do this. So nuclear reactions use superscript and subscript numbers. Superscript are the top numbers, subscript are the bottom numbers, and those show the mass number and the atomic number. The totals for each of those must be the same on both sides of the equation. It's going to be easier when you actually look at it. So here's an example of alpha decay. If you notice, we have uranium with a mass of 238, that's the top number, atomic number 92. If it undergoes alpha decay, that means that alpha particle comes off. The alpha particle, remember, has a mass of 4 and an atomic number of 2. Well, if we add the numbers up across and on the bottom as well, we treat the arrow like an equal sign. It's 238 equals 234 plus 4. Checks out. If we look at 92 equals 90 plus 2, that checks out also. And remember, when you're trying to figure out what the new element is, you just look at what the atomic number is. In this case, 90 is thorium. So that's a good way to actually look at this. So now we look at beta decay. On one side of the arrow is carbon-14 with an atomic number of 6. After it undergoes beta decay, it decays into nitrogen-14. Make sure that everything adds up. 14 equals 14 plus 0, check. 6 equals 7 plus a negative 1. Well, that is 7 minus 1, which is 6. So all checks out here for beta decay. As far as gamma decay goes, just gamma rays are emitted as energy, and there is no change in the element, so we don't have to worry about balancing that equation whatsoever. So make sure you practice with those. Here are your key terms. Good luck, and we'll see you in the next unit.